You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Natalie Wolfenbarger. Natalie Wolfenbarger received her geophysics doctoral degree at the Jackson School of Geosciences. An aerospace engineering graduate, her research has evolved from characterizing spacecraft performance to examining how data acquired by spacecraft can be used to better understand Earth and other ocean worlds, particularly Jupiter's ice-covered moon, Europa. She is currently an affiliate member of the Europa Clipper science team supporting verification and validation of the REASON instrument, an ice-penetrating radar designed to peer through Europa's enigmatic ice shell. Her research aims to understand how we can use radar studies on Earth ice to help interpret future data collected by REASON to investigate Europa's habitability. Her studies of analog environments for Europa has led her to both the Arctic and Antarctica. Remember to subscribe to Event Horizon so you never miss an episode.
Natalie Wolfenbarger, welcome to the program.
Thank you. Happy to be here.
Now, you recently released some findings about studying ice in Antarctica and how ice accumulates and behaves, and how this might relate to the subsurface ocean of Europa. Can you give us an overview of that work?
Yeah, absolutely. So one of the problems I was interested in is what is the salinity of Europa's ice shell? And one of the reasons I was interested in this is we have a mission that's going to go explore Europa, a NASA mission called Europa Clipper. And one of the instruments on it is an ice-penetrating radar. What this means is basically we're going to send energy down into the ice and try to understand what's beneath, whether it's water or something else. And one of the things that can affect that signal is salts in the ice shell. What I wanted to look at is, can we use what we understand for the formation of ice on Earth and apply that to moons like Europa or Enceladus? And what I basically realized was, although we see these kind of extreme conditions at the surfaces of these worlds, when we look at what the conditions like temperature and pressure could be at the ice-ocean interface, this is actually not too different than what we see beneath ice shelves in Antarctica. And so I basically went back to Antarctica and to the literature that we use to understand ice and kind of use that to guide some hypotheses for what we expect the ice shell to look like.
So even if the salinity is high in these oceans, the fact that there may be ice forming in them would suggest that's lower salinity, right, usually?
That's a great question. Yeah, so when we have salty water, like ocean water, we expect that to start forming ice at a lower temperature. So for seawater on Earth, that's about -2 degrees Celsius. But what ends up happening is when this ice is forming, because you're getting heat being conducted away from the ocean due to, let's say, atmospheric cooling, you actually do still trap some salts in the ice itself. And so over time, if you have like a fixed volume, for example, as you're freezing that volume of salty water, that salty water can also become more concentrated. And so there is kind of this play between temperature, salinity, and under what conditions ice actually forms.
Now, on Earth, in Antarctica, under these conditions, I mean, what does that look like? If you were watching ice forming in the ocean, I mean, what would it look like and how would it behave?
That's a great question. And I've actually often looked up, YouTube videos to try and kind of see what people have recorded in terms of ice forming, particularly in places like Antarctica. And what's kind of cool is we have these two different ways that ice can form. One of these ways is similar to maybe what you'd see in an ice cube tray in your freezer. It's this directional freezing process known as congelation growth. And so what's basically happening is as this water is cooling, you have ice thickening in one direction. And when it's sea ice, you can actually form these really cool brine channels. So there's this awesome BBC documentary that has this Brinicles of Death or something like that, where you basically can see all of the salty water being rejected from the ice as it's forming. And so that's one way that you can have this ice form. But another really cool way is this frazzle ice formation mechanism. And this is kind of what I think the article referred to as a kind of underwater snow. And in this case, you actually get these little crystals of pure ice that can form beneath the ice shelf. And they float up and collect beneath the ice shelf in cracks and regions of local thinning. And so that's something that, like, I hope one day I'll have the opportunity to see. But as far as I know, there's no video of this actually happening beneath ice shelves. Or if there is, I just haven't seen it.
It'd be amazing to see it because it's sort of a upside down snow, really.
Totally, yeah.
Now, this would accumulate this sort of upside down snowfall. So on the interior of an ice shell moon, you would have a zone of sort of accumulating snow right beneath the ice shell, which is interesting because that sort of reverses the process of snow on land, at least here on Earth, right?
Absolutely, yeah. And in fact, we kind of, like we see this transition of snow into glaciers on Earth, where it's kind of light and porous and then slowly becomes more consolidated. This is something that we see beneath ice shelves as well. This kind of upside down snow is really a good analog in that sense, because you have where these ice crystals are buoyant and like basically pushing up on the crystals that are above them. You get it kind of this consolidated layer that transitions to a less and less consolidated layer as you go further in depth, just because it doesn't have that buoyancy forcing as much. So very much a good analog to snow.
Could this work as a record of essentially this ocean at Europa or Enceladus? Could it serve as a sort of geologic record of, just like glaciers do here, where everything's layered and you can go and study Earth's climate in the past by doing ice cores? Is it possible that we could drill ice cores on any of these ice shell moons and determine the conditions of the ocean beneath without having to drill into it?
That's a really beautiful question. And definitely something that I've thought a lot about. I think it would be interesting for us to be able to take something like an ice core on a moon like Europa. But where the problem is these are extremely thick ice shells, like on the order of kilometers thick. So if you wanted to get kind of a snapshot of what this might look like over the moon's history, you would kind of necessarily have to drill through kilometers of ice to get to kind of a representative historical record.
I wonder if you could make use of the sort of active geology of say, Europa particularly, because it looks to have had periods where the ice is shattered and you had liquid water refreezing and things like that, sort of like almost like plate tectonics, but in ice. Could you take advantage of certain localized sites that might preserve like a strata of what's going on with the snow accumulation underneath the ice shell?
That's, a really insightful point. Particularly certain features like we call it chaos. In particular, looks like there's kind of been cracking and then maybe even injection of brine-like material into the surface. So I think you could make the argument that maybe certain features associated with resurfacing or interaction with the subsurface might be interesting candidates for getting at this record. But then you also have this complication of we don't really know how the subsurface was altered by these processes, right? So are you getting a pristine record or a record of, different physics happening in the shell that might alter the chemical signature or the salinity? So it's a really compelling question, but something, that we really wouldn't know until we looked.
See, that just goes to show how early we are in the game of studying these ice shell moons. And it almost reminds me of geology because things can change. Pressures, temperatures, exposure to the sun, all sorts of different factors could alter what you're looking at. And it's going to be fascinating as we explore these worlds to actually see that, because it will be every bit as complicated as these processes are here on Earth. There is a lot to learn.
Absolutely, yes, absolutely.
Now, another interesting aspect of this finding is that if that snow is accumulating, there's going to be a sort of fuzzy area where it's not very dense yet. And such environments might possibly be conducive for microbial life to hang out in, right?
Yes, exactly. I will say I actually, in the process of having a paper reviewed that is tackling exactly this question of when we have these kind of briny ice environments, what does this imply as a potential habitat for organisms that could be potentially more accessible than the sub-ice ocean in terms of future life detection missions? And so I think you're spot on that this question of like, if you have more permeable ice, like what does this imply for, potential life is the right way to look at this question. And we're kind of just getting there. Like we have a lot of insights from sea ice on Earth, but I think bridging them over to what we might expect at the ice-ocean interfaces of these other worlds is still very much a work in progress. But I agree with you that I think that's kind of a compelling site for biosignature detection or habitats beneath the ice shell.
Now, again, with drilling into these moons, not only is it hard, it's very hard to send a spacecraft out that remotely is going to drill down into these things or melt its way into these things. But there's also the question of contamination and not really wanting to bust into the ice shell moon unless you absolutely have to. So looking at the surface and looking for this geologic record, or whatever you would call it, is the way to go first, right? Before we try and start thinking about drilling in there. In other words, we need a sample return mission before we need a drill. Would you agree with that?
That's a great question. And it's kind of a tough one for me because there is this desire to just go do it, right? There are levels of preparation that you can do in terms of landing site selection. That could be something you can do with completely remote instruments. But there's also this question of, if we're putting in the resources to go explore these worlds and our objective is to get to the subsurface or to sample biosignatures, I guess this is, the selfish part of me of like, how long do I really want to wait to see this? And this is work that's been going on, for decades, probably before I could even read. But I do think it's a question that we can ask ourselves, and even in the context of Mars, is what steps are necessary to take to get where we need to go versus, like truly the most conservative from the perspective of engineering. So this is actually, I studied engineering in college, and there's these two competing sides of my perspective on this. The one that, as the engineer, that says, we want to make sure we do this right. We're investing a lot in this. Let's take gradual steps to get where we want to go. And then the scientist in me who just wants to see what's under the ice. And I don't think either of those perspectives are wrong. They're just different philosophies on this problem that's bigger than any single discipline,
Well, I won't lie. I think about it all the time, what could be in that ocean. Now, microbial life would be amazing in itself, but if there's something bigger in there, I'm not really suggesting Europa and space whales or anything, but maybe there's a chance of something.
Yeah, I mean, it really does come down to like this balance of what energy is actually available to life there. And so the more constraints that we have on that, the more of an idea we can have on, do we expect these tiny isolated microbes or potentially more complex life? And I will say this isn't really my area of expertise, but I absolutely have read papers that are kind of exploring this energy budget and what this means for the type of life that may be down there. So yeah, it's kind of an open question of what could really be there.
Now, investigating the thickness of the ice, that's going to be something that's big. What's that look like? I mean, when you're getting a spacecraft ready to sort of radar through an ice shell moon, what's the engineering of that like?
That's it's difficult, I guess to say. One of the issues is we don't have the best constraints currently on how thick we expect the shell to be. Some estimates are on the order of kilometers, others are up to, I think 90 kilometers is the largest estimate I've seen from a modeling paper. So when you're trying to design an instrument that can provide constraints on the thickness of the shell, there's this balance of what is the right instrument to answer this question. And one of the cool things about Clipper is we kind of have two ways of getting at this answer. One is the ice penetrating radar, which can basically peer through the ice, but it might not peer all the way down to the ice-ocean interface. This is kind of a question of what are the properties of the shell and how thick it actually is. There's also the magnetometer instrument. And this one is kind of an indirect constraint that we can get on the ice shell thickness, in that it's kind of convolved with the electrical conductivity of the ocean itself. So with these two instruments, there's the opportunity to kind of either get a bound on what the ice shell thickness is, if we get like an isolated reflector from the ice shell interior, and then maybe another bound from the magnetometer data. So what was kind of clever about this mission is they do take in mind these kind of end members of, is it a thin shell versus a thick shell, and what's the right instrument for that? And so from the engineering standpoint, there was a lot of thought that went into, there's a lot of uncertainty, and how can we bound this problem? Which is a long-winded answer, I apologize.
Oh, I'm a talk show host. I love long-winded answers. It means I have to talk less. Now, variability in the thickness of the ice. Are you expecting that there's going to be different thicknesses? I know that might be strongly suspected for Enceladus, but do you expect that for Europa as well?
Great question. There are papers that argue that you might expect the ice kind of to flow and equalize in thickness at the base, and so that wouldn't necessarily provide, allow for differences in ice shell thickness to be sustained. Then you have other works that look at ocean heating that say, like, well, we expect the heat to be elevated here, so fundamentally that translates to a thinner equilibrium ice shell thickness. And then other people that argue for cracking at the base of the shell. So I guess in summary, the answer is we really don't know. It's likely not as pronounced as Enceladus, but this is a question that we can answer with the data from future missions.
Now, would you have zones where ice formation is favored? For example, right underneath a fissure or something like that. Is that expected that there would be differences in sort of the weather, so to speak, and it snows harder in some places than others, right?
Definitely, yes. So one of the cool things that we do see looking at ice shelves in Antarctica is where we have these cracks, we do see this kind of what's called an ice pump, basically this process of melting and then refreezing where it's shallow, which is kind of the driver for this underwater snow. So we might expect that process to be occurring there. But you also have this competing process of, you have these, if you were to have a fracture at the base of the shell, you're now introducing ocean water into a very cold environment. So there are kind of these two processes that can operate to refreeze there.
Now, the origin of the snow, is it at some deep level, or does it actually originate down and near or on the ocean floor itself?
That's a great question. So the mechanism that we discuss is kind of an ice recycling process. So really it's ice melting that refreezes somewhere else. So it's not really originating from the base of the ocean. However, there are some really interesting studies that have been published, on Ganymede, for instance, where you have these high pressure ices. And so there have actually been papers that propose that you might similarly have this underwater snow operating on worlds like this, but there it's actually a competition between these different phases of high pressure ice. The lead author on this paper is Steve Vance at JPL, and it's a really interesting paper, yeah.
Now, you've worked in Antarctica, right?
I did, yeah. I was lucky enough to be able to go down on an expedition that was supporting the collection of ice-penetrating radar around Thwaites Glacier. And that was the first time that I got to go, and hopefully not the last time.
What was that like? Were you actually at a scientific settlement, or were you just out basically camping on the ice? How did it work?
Yeah, it was a really great opportunity. I actually got to camp on the ice. So we went down with the Korean Polar Research Institute, COPRI, and we were on their icebreaker, the Aron. And we, how long did it take us to get down there? Probably a couple of weeks to get down to Antarctica. And then we had these 2 helicopters on the icebreaker that basically transported us and our equipment to Thwaites Glacier, where we were able to set up camp and kind of use that as a base to to do these other aerogeophysical surveys. And I will also highlight that we were just a small part of this much larger expedition that studied oceanography, set up GPS stations, and it was really cool to be a part of that and to actually kind of be on the ice in an environment that could be Europa, maybe.
Something similar, perhaps. I would imagine more similar than dissimilar, anyway.
Yeah.
What was the weather like? What was the temperatures like, and what season was it?
Yeah, so we go down there typically around, I guess, when it's warmer, so not wintertime, closer to summertime. And one of the things that really struck me when we were out on the ice was how warm it actually was. So when we think about Antarctica, we think, oh, it's minus 50 even Celsius. And because these ice shelves are bordering the ocean, it can be quite a bit warmer. And so there were actually quite a few days when we were right around freezing, which doesn't bode well for melting of the ice shelf. But yeah, then most of the time we were there, actually, we had pretty high winds and cloud, which made it difficult to do our surveys. So the days that we didn't have a lot of wind and we had clear skies were the days where we could actually do work. So a lot of our time was spent really just waiting on weather, which was, again, kind of warm relative to what I was expecting.
Might seem like an odd question, but my background is amateur astronomy. It's been a love of mine since I was a kid. Did you get a chance to look at the Antarctic night sky, and what was it like?
I did not, unfortunately. There was too much light for summertime. So we had, I think when we were leaving, the sun was just starting to kind of like hang out around the horizon. But for the most part, it wasn't too dark. When we came out away from the ice shelf and we were in the Southern Ocean, then we started having kind of like true darker skies. And I do remember vividly just like, yeah, how amazing it was to experience that kind of darkness and see the stars there. So
I guess very few people ever get to see the Antarctic night sky because of the 6 months light, 6 months dark. And when it gets dark, it's winter. And I guess there's not that many people that go down there other than skeleton crews and things like that during that season, unfortunately.
Yes, them and also the people I think that study neutrinos get to experience that. I honestly would love the opportunity. And I've heard so many people tell me, like, you think you would, but no, it's really hard. But I kind of share your love of the stars, and I think it would be just, yeah, such an incredible thing to experience.
All right, Natalie, we are out of time, and I wish you great luck in your work, and I hope you'll come back sometime next time you release a paper or something like that on the ice shell moons.
Absolutely. Thank you so much for having me. This was a lot of fun.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice. What a really great interview. Hey, Aaron, have you ever wondered if alternate universes exist?
No, not really. It's not really something you could prove, so ultimately, does it even matter?
Yeah, probably not, I know, but I just can't shake the feeling that there might be more to this. Like I might be in the wrong reality, or the right one.
Whatever, so they've heard this gag 3 times now, so I'm gonna go. Pay me.
Wait a minute, it was an alternate reality. The possum has gained control over the many worlds interpretation of quantum mechanics.
Yes, John. And it seems one of my iterations actually gets paid.
Yeah, none of mine do.